So here I'm going to talk about Bayes' theorem and tree diagrams and how tree diagrams are a great tool to make sure you're accounting for all the different possibilities, and then you can answer questions about conditional probabilities, which is what Bayes' theorem is all about. So let's look at an example of, let's say we're drawing some cards from a deck as an example. And all we care about here are the different suits that you could draw. So let's draw four cards and let's try to find the probability of getting a flush. So, flush meaning all four of the cards are the same suit. So, this represents drawing the first card, and we could have diamonds, we could have hearts, we could have spades, or we could have clubs. So those are the four different suits. They're equally likely. They each have a one-fourth probability of happening. I'm going to actually write that instead out of 52 cards. So if there's one-fourth of the cards are each suit, that means you've got a 13 out of 52 probability for any of those to happen. Okay. What you can do next then is we're going to draw four cards. So this is going to get a little bit wild. What you can do is recognize that it's going to be the same as we go down. And so I'm going to only draw out several of the branches, and you just have to understand that the rest of the branches would be identical. So this represents drawing the second card: diamonds, hearts, spades, clubs, diamonds, hearts, spades, clubs, diamonds, hearts, spades, clubs, diamonds, hearts, spades, clubs. So you can see how if we go to four different draws of the card, it's going to get really, really messy. What I want you to focus on is how the probabilities change for the second draw, however. If I drew a diamond, so if I'm on this top branch, if I drew a diamond, that means that there's not 13 diamonds left in the deck. There's only 12 diamonds because I already have one of them drawn out of the deck. So that means there's a remaining 12 out of, there's not 52 cards anymore, 12 out of 51. If I draw a diamond in my first one and then a heart, well, there's 13 hearts out of the 51 cards. 13 out of 51. 13 out of 51, like that. Okay? Similar idea if I go heart first and then diamond. So this branch here, heart, and then diamond. There's 13 diamonds out of 51. It's only the one that goes heart, heart. That's 12 out of 51. Heart, spade, 12 out of 51. Heart, club, 12 out of 51. And you can see how the other probabilities would match up as well. I'm going to return back up to just doing the top one. We can draw four branches off of the diamond. Diamond, heart, spade, club. How many diamonds are left? 11 out of 50. How many hearts are left? If I drew two diamonds before that, there's still 13. So this says 11 out of 50. And then the other three branches are 13 out of 50, 13 out of 50, 13 out of 50. If I wanted to, I could draw all of these other intermediate ones. By the way, if I went diamond, heart, diamond, then I drew one diamond. So there's 12 remaining out of 50. If I drew a diamond and then a heart, there's 12 remaining out of 50. If I drew a diamond and a heart and then a spade, there's 13 out of 50. And here there's 13 out of 50. I'm going to pause here for a second and just remind you that the total probabilities need to add up to 1 at each of the generations of the tree. So I'm going to start circling things that have to add up to 1. These all need to add up to 1. And if you check it, 13 plus 13 plus 13 plus 13 makes 52. These all need to add up to 1. And if you check, 12 plus 13 plus 13 plus 13 makes 51. Same idea right here. 12 plus 12 is 24. 13 plus 13 is 26. Here, these need to add up to 50. And they do, as you can check. So let's just do one more branch, and then we'll just use symmetry to like figure out what it would be for any of the flushes. So if I do one more set of branches here, I've drawn 1 diamond, 2 diamonds, 3 diamonds, so there's 10 diamonds remaining out of 49. If I went diamond, 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 and then a heart, there's 13 out of 49, 13 spades out of 49, 13 clubs out of 49 remaining cards. And of course, there's this whole mess of other branches here that I'm just choosing not to draw because nobody wants to see me draw that many branches. So what would be the probability of getting 4 diamonds in a row? Well, that would be multiplying the probability of all of the other diamonds, of all the branches of diamonds. So we have 13 over 52 times 12 over 51 times 11 over 50 times 10 over 49 right there. And you should recognize this probability as really similar to factorials, with a lot of the terms canceled out. And that's because what we're really doing here is choosing values. You can represent the probability of choosing 4 diamonds like that, or you could represent it in this way. You have 13 diamonds that you're choosing 4 of, so that's going to cancel out all of the 9, 8, 7, 6, 5, 4, 3, 2, 1. And over here you have 52, choose 4, and that's going to cancel out 48 and below, and then the extra 4 factorial cancels out on the top and the bottom. But the probability of 4 diamonds is a little bit less than the probability of a flush. The probability of a flush is going to be, there are 4 different ways, 4 different suits that you could have done. So it's just 4 times the probability of 4 diamonds. Okay. So I want to talk a little bit about Bayes' theorem. And Bayes' theorem is the probability that something happens given that something else has already happened. And so you can think about this as being at a later branch along the way. So for example, the probability of drawing a heart given that you already drew a diamond has to be 13 over 51, because that is the probability that's at the end of that branch right there. And what the other way you can calculate this is by using Bayes' theorem. Bayes' theorem. What's the probability of drawing a heart? Let's see. I'm going to write this in backwards order, because really what I'm talking about is drawing the 2 cards in order. So what's the probability of drawing a diamond, then a heart, given that you already drew a diamond? So the way you read that is the vertical line, you use the word given. And so the thing after the vertical line has already occurred. And you're looking at the probability of the first thing happening given that the second thing happened. Well, we know the answer is 13 over 51. But the way that you can calculate that probability is, what's the probability of drawing a diamond and a heart? So that's multiplying 13 over 52 times 13 over 51 divided by what's the probability of drawing a diamond in the first row, 13 over 52. So those two things cancel out, leaving you with the probability that I circled earlier. So tree diagrams give you a way of just enumerating all the different possibilities, and each of the possibilities that happens later along in the tree diagram represents a conditional probability. If you want to find the absolute probability, you have to multiply as you go along the branches. So that's why the probability of drawing a diamond and then a heart is the probability of drawing a diamond in the first one times the probability of drawing a heart. Maybe I'll write like this: diamond in the first generation, heart in the second generation, right there. You multiply the probabilities there. But if you do a given probability, you can just use the probability that's sitting right there at the end of the branch. So that's a little bit of an overview of tree diagrams. The formula that you can use for Bayes' theorem that I used right here, I didn't spell it out necessarily. The formula is that the probability of one thing happening given another thing is the probability of them both happening divided by the probability of B. So there you go. Please comment. Let me know if you have questions or if there are other examples that you want me to do. Thanks for watching.